And we can start the discussion. So I will ask for the three speakers of this morning to come on stage. So Alessia, Catarina, and Sylvain. And I hope Marta is still online.
Yes.
Perfect. Okay, so we can, I think, start this discussion about massive black hole. That was a topic of this morning session. So I'm pretty sure there are plenty of questions from the room. So we'll let the stage to people in the room if they want to ask a question about this topic. Yeah.
Please do forgive me if this is really stupid. So I got a little lost in all the different timescales that are appearing in the different stages. So is there the possibility, essentially, for the EM observations and LISA to co-interact in the sense that you get some data from the EM that says, hey, we think this thing is going to merge in the next handful of years. That can then inform, one of the earlier talks was showing all the problems of the biases in the LISA fitting, but now you've got some EM constraints on that, which maybe improves the LISA stuff. That then, in turn, gives you back better system parameters that can feed into your EM, and you get this beautiful virtuous circle. Or do the timescales not work out? Because I kind of felt like the EM stuff, probably all the signals were too early for a LISA timescale, but I may have got lost in there. Do you see what I mean?
Yeah. No, I see what you mean. Can you hear me? Yeah. So yeah, it's very interesting, and I think so. If you can find candidates, I would say at milliparsec separations, then that's something that you can actually do. If you go towards the merger, then it gets progressively harder to use the synergy between the two. But yeah, that would be the ideal scenario. Yes. I don't know if any other.
And it's plausible electromagnetically to get the milliparsec doodars, to find them at milliparsec separations.
Yes.
Okay.
Yes.
Right.
Yes.
That's the bit I.
Again, you need a smoking gun. So you need at least 2 techniques, I would say, or you can. Yeah.
Okay.
Like if Vera Rubin lasts for more than 10 years, I think we have more chances, of course. But
it's not in space. So to me, that means it should do. But what?
Yes.
Thank you.
Maybe I can add that especially for the massive systems, almost all of the information about scalar localization is going to come from the merger, which means that it's very important to understand what we can do with follow-up observations. So it's going to be, in that scenario, it's basically LISA first, an error box of, say, 1 square degree or even better. And then the question is what you can do after. So you can point your telescopes here, but then if you want to have any form of comparison between pre and post-merger emission, you will need to go to archival data for before and try to hope that it's good enough that you can see the difference with the post-merger. Not an observer, looks challenging.
Yes, the issue here is really to have, because you say 1 degree or even less or even smaller, but 1 degree and deep is difficult to have. So to have a facility that can scan deeply 1 degree square, 1 degree square is huge for, depending, of course, on the frequency domain you're interested in. But for example, if you go to the optical, there is already Vera Rubin that can do something like that. And still, very likely is not deep enough. So I don't know. It's not so easy to be able to detect the electromagnetic counterpart also for the reason you said that you need to have a comparison image and so on. This is also very, very important, but is also observationally difficult in this sense.
I agree.
I don't know if okay, so I will add something. That for some binaries at low redshift and in the sweet spot for the mass, you can get much better sky localization. So it's At the moment, models don't predict a huge merger rate for LISA at low redshift, say redshift 1, but we may be pessimistic. And in that case, it would be much easier to get the binaries. I mean, Monica Colpi has worked on this a little bit, showing these platinum binaries that do exist and for which this localization is much easier.
Okay, thanks, Marta. More topic to be discussed. Maybe I can at some point that would like to have your opinion. What could be in fact the synergy, because LISA will be in 10 years. So what could be the synergy with the facility that we'll have by this time? I was thinking about the ELT, maybe new antenna, SKA. So what's your opinion about which synergy could be used to better understand black hole evolution using both gravitational waves and electromagnetic radiation?
If you're talking about the supermassive black holes, I mean, I think that one of the only ways is to in these 10 years, if we manage to identify a single supermassive black hole binaries in PTAs, then of course, I mean, in theory, what we assume is that PTAs will be the stage before the LISA one. So, of course, I mean, you will never see the transition between the PTA band and the LISA band. But I think that the only way to get some observational hint for this is to get it a single massive black hole binary in the PTA band, I guess.
But well, between PTA and LISA, we are fairly segregated and separated in mass, right? So I'm not sure what the lowest mass we can expect to detect in PTA. In LISA, we're sensitive up to fairly high masses, but the astrophysical rate, at least for the model I've seen, is also very low. You could, in principle, see something at several 10 to the 8 solar masses, but barely see it. And it will really look like a one cycle of look like an instrumental glitch, basically. But if you compute the SNR for it, it will still be relatively large. But if you plug in the astrophysical catalogs, as I was presenting before, you get really a few possible events at 10 to the 8 and not much more. And the bulk of the population comes from 10 to the 5 to 10 to the 6, depending on the models. And we're even sensitive to much lower masses than this. So there's also something that is not clear to me is assume we have PTA detections. They probe a lot of astrophysics, but not of the same scales as the LISA population. It's massive black hole binaries, but from 10 to the 5 to 10 to the 9, you have 4 orders of magnitude. It's not exactly the same physics. So can we take the information that we get from the PTA, say, level of stochastic background and take the information to infer a LISA rate?
Yeah.
Yes, that's a question.
So,
like to know the opinion of Marta on this question in particular.
Okay, so do you want me to say something, Antoine? Okay, okay. So I don't think we can extrapolate naively, but I think that as we move on, we should try to have models that are self-consistent. And for the most, in general, the type of models that we have that are cosmological are of two kinds. One is semi-analytical, the other one is simulations. Semi-analytical, you can get, PTA and LISA kind of with the same approach, but you have to make simplifications. With cosmological simulations, you have much more information, but usually you're limited to either PTA or LISA simply because of the volume resolution dichotomy. So I would say that at the moment, I don't feel comfortable extrapolating. I feel the semi-analytical models are giving a picture that is complex for the mainly because it's very hard to get to the PTA amplitude. So I feel that the first thing I would really like is to see how stable the results of PTA are, and then we can start to say, let's anchor what we see at low redshift and see what happens at high redshift. I mean, or as the low masses. So the other thing, going to what Sylvain was saying, I think that something that is really important is really to characterize variability, and so something that we may consider a transient or a periodic source, it may just be a variable AGN, and especially when we go to low masses. I think that for PTA in some sense is easier because they are very massive, they're in the range of standard quasars, although I'm not sure that PTA binaries are in the quasar regime. My feeling is that they're not strong accretors. But I really hoping that in the next 10 years, we can characterize low mass black holes, 10 to the 5, 10 to the 6, electromagnetically much better than we have today, although of course we have started, I mean, there are people in the room who have worked on intermediate mass black holes and helped a lot of our understanding. But really trying to pin down the properties of low mass black holes and low mass galaxies, and then we can try to hope to interpret what we see with LISA.
Yeah, so maybe to continue on this topic, you were talking about low mass black hole located in low mass galaxies. So this is almost terra incognita so far. So what progress can we expect before the LISA fly on this topic, both on the simulation and observation side? Would you comment on that? What's your opinion, both on observation and simulation? What progress can be expected?
So from the observational side, I think that, I mean, the progress in the last few years has been amazing. I mean, going from 0, it's not very difficult. So now we have samples of low mass black holes at low redshift. They're still very much not well characterized, obviously because it's hard. But I'm hoping that, with more interest in this area, more people will try to work on this. Tau disruption events will help a lot. I mean, LSST is going to detect many tau disruption events at low redshift. Of course, you can extrapolate the physics of TDEs to standard AGN, but at least we will learn more about the population. From the simulation point of view, really we have, as a whole, as a field, developed many new techniques, both from the cosmological side, but also circumbinary disk. I mean, Alessia and Rafael showed these beautiful simulations. And I think we could significantly improve. There, we should talk a little bit more, groups working on different scales, to try and see where we fail in predicting, say, the connection between galaxy scales and circumbinary disk scales. But also, as I said in my talk, there are so many uncertainties that I think it has to work, a joint evolution of simulations and observations as they look at each other. I mean, the high redshift black holes with JWST have been my nightmare for the past year. I mean, I love them. It's been the most exciting time of my life, but we don't understand them. We cannot characterize them very well observationally, and theoretically, then what is my anchor? I'm a theorist who usually anchors to observations. So I usually say, okay, my simulation is wrong because I'm 5 orders of magnitude away from observations. And now the observers say, oh, sorry, yes, actually these 5 orders of magnitude, they were correct. It's just that we didn't see this AGN before. So right now I'm kind of in a situation in which I'm waiting, staring for results to settle, both PTA and JWST, and then see what with simulations where we can anchor our results and move to more terra incognita.
Thank you, Marta. So more comments on this topic, or?
I had maybe a question for people doing simulations at low masses. So this is a very ignorant question, sorry, but on the gravitational wave side, everything is beautiful. There is no scale in the system, so if you ask for 10 to the 3 or 10 to the 7 solar mass black hole, as long as there is no matter, there is no problem. It is the same physics. But what about accretion disk and all this complicated physics? Is it basically the same physics at intermediate mass black holes and massive black holes and supermassive black holes? Or are there really things that change qualitatively along the way?
I mean, what I can say is that at the level we are performing these simulations right now, so where we include not a lot of physics, I would say it's the same. So like in principle, if you're assuming that your disk is like isothermal and completely smooth, then you can do scale-free simulations. So you can apply the same results to stellar mass binaries, star binaries, massive black hole binaries, intermediate mass binaries. I think what will change is if, larger scale simulation can tell us how the material is distributed for different masses, which is a big assumption that we make, that the disk contains that mass and it's distributed that way around the binary. So this, we assume it's valid for every scale, but we would need some indication from larger scale to see whether that's the case.
May I ask another question following this to Alessia and perhaps Raphael? So as we go more in the PTA band, 10 to the 8, 10 to the 9 solar mass black holes, a thresh shift less than 1. I think that a significant fraction of the population will be in the ADAF regime, meaning that the accretion disk itself will be different. I've been asking to Sophie Kudmani, who has done some simulations, but she said that when they go in the ADAF regime, they don't change the structure of the accretion disk; they only change the emission. So, is there any hope to try and include accretion disk from the sub-Eddington to the mild Eddington to the super-Eddington regime in this type of circumbinary disk simulations?
I think in principle, yes, you would just need to include more physics. But yeah, I'm not aware of anyone who is doing that. I know that Sophie is basically bridging different scales, but again, using prescriptions from one scale to another. So it's so yeah, I mean that would be the hope, but I don't think there is any effort in that sense right now. At least that I know of. Maybe I don't know if Raphael has something else.
You have a question to address to the speaker or general interest?
I have a question about the electromagnetic observation and so before LISA or for PTA, what will be the instrument, what will be the survey that will bring new information? Because from the talk that I saw this morning, we start to have some idea of the feature we had previously, but now it's more and more precise. We start to have some idea of the feature that we would like to find that will characterize the double or a binary. But so there is Vera Rubin, that will observe things. We have these two catalogs that we already mentioned this morning, the Catalina's real-time survey and the ZTF, but we can do more with this catalog as continues the work of Vincent. There are more to do on that side. We need new catalog. What is the status of that? Question is for everybody, maybe Nathalie.
Yeah, I think it's a good question. Ruben, I think, is the way we should be going forward. I mean, obviously, CRTS is finished. I don't think there's a huge amount more you can do. It's useful though if you do find some source that's varying today, you maybe want to go back and look at that Catalina data. Ruben, I really believe we will find these things. You'll find them on shorter periods because the cadence will probably be better, and you'll also get a much better precision with the photometry. So we've been working with the Fink broker to try and put together some kind of module that goes into the data stream and then try to detect these variable objects that might well be massive black hole binaries. Another thing that Vincent sort of mentioned was that we've also tried to do this with X-ray, but this is different. So at the moment, we've been using XMM Newton. And XMM has got a maximum length of an observation of 130 kiloseconds, so it's about 40 hours if those kiloseconds don't speak to you. So you can only look for very short period binaries, and there's been some very promising results. We found some galaxies that shown quite significant periodicities. So these are sources that are actually obviously very close. I guess there's probably other wavelengths that could be exploited. I mean, this mentioned earlier, maybe Fermi. It's not something I've personally looked into. I don't know if there are people here that have done anything with Fermi, but yeah, indeed, it's interesting because it covers the whole sky. So yeah, you're probably less biased about what you're looking at. I think, yes, SKA will be useful. It depends what you're actually going to be looking at. I presume you're going to be looking at the jet. Then you're going to see the processing of the jet. But I think we heard this earlier. I mean, procession of a jet can happen because of a binary system, but it can also just happen because of procession within an accretion disk anyway. So I think it'd be difficult to deconvolve the two, but I'm sure it's possible. I haven't personally looked into it more. Maybe you know something or someone else.
Yeah, perhaps SKA radio can be coupled with some other techniques on the same object.
Yeah, absolutely.
That could serve just like an indication of, oh, you should look into this.
But I agree. I think it was you that said earlier on, you need to have more than one observation with one methodology. You need to have 2, 3, 4, 5. So I mean, if you can go across the whole of the electromagnetic band and then maybe some multi-messenger data as well, I think you're cool.
If I may, because so I have a comment, the question in the sense that you mentioned that they have Catalina and so on, but the issue is, do you need to go, how deep do you need to go to have a useful information? I mean, because there is there are ongoing sky surveys and so on, but the problem is really if as shallow as ZTF is fine with you or not, because that's why I mentioned SKA or and Vera Rubin and LSST for sure. There is really a huge difference from what we know now in sky survey, in the optical and in the radio, and what we will know with the LSST and with the SKA in terms really on the sensitivities of such instruments. So there is a jump in depth. So do you need it? Not, because if you need it, those are the two things that will do this jump. If not, and there are the only two in my mind.
Yeah, the only two that I have in mind at the moment. But yeah, I think, Ruben, we definitely need it. We definitely need this precision with the magnitude, and that's what you're going to get because you've got a bigger telescope. With the work we've done with Vincent, it's he already told you you can't validate completely these binaries because the data quality is poor. I'd say it's not that poor. just for this kind of work, it's poor. So yeah, you definitely need Rubin in that case. I mean, SKA would definitely be interesting to look at. I just don't know a lot about the cadence either that SKA is going to come back to each field. And I think that's important too. I'll let the panel speak.
Still have a few minutes left before closing the discussion. Another topic to address? Last chance. Okay, everybody is a bit tired. Otherwise, we can close the discussion. And really, thanks again all the speakers of this morning. Very nice talk. And we reconvene at 2 o'clock. 2:40. Okay.
Just a quick announcement about the lunch.